lectures since last October. And his research interests include quantum many-body systems, in particular their factor equilibrium dynamics in presence of driving dissipation, so something I guess many of us are interested in. And until the last October, he was a Stephen Hawking postdoctoral fellow at the Theory of Condensed Matter group at the University of Cambridge for 4 years. And previously he was a postdoc for 2.5 years between Oxford, Paris, and Chicago. And Orazio carried out his PhD at the Institute of Theoretical Physics at Paris-Saclay, and where he graduated in 2019. So, Orazio, now the floor is yours, and we are happy to hear your talk.
Thank you, Federico. Thank you very much for the invitation and for the introduction. So I'm glad that you invited me for this talk. I hope you find this interesting. So if you confirm that you're hearing me correctly, I'll just start and go for the presentation.
Yes.
Okay, very well. Okay, so I'll talk about some work that I've been doing while in Cambridge, so up until last month, mainly with Professor Nigel Cooper as a collaborator. This is about atomic arrays in strongly correlated regimes. So just let me just start to set the stage of how I think about this system and the kind of, the point of view I'm using to approach this system, which is that of quantum phases and many-body physics. So I'm interested in seeking out phenomena in which I have many quantum particles that somehow behave as a whole collectively. And so this is typically what people have studied for ages, in particular in condensed matter physics. For example, here I'm showing this phase diagram of a cuprate with several different quantum orders, some of them more subtle than others. And typically in condensed matter until, let's say, 30 years ago, one could probe these collective phenomena in quantum physics only in equilibrium systems at very low temperatures, because, well, in the solid state is where coherence could be maintained on a large enough scale, such as to really have truly interacting quantum physics. But in the last decades, let's say 3 decades, there has been a lot of progress in controlling quantum systems. And nowadays, we can do much more. In particular, we can induce and probe the dynamics of many particle quantum systems, such that they remain quantum even in the dynamics. And there is, which is the main difficulty really, because when you start moving things, then things decohere very quickly. But nowadays we have several platforms, both in solid state, so materials you can do ultra-fast quantum probe to measure things on excite and measure things on very short time scales. But also we have several synthetic platforms in which we can really assemble some sort of artificial matter atom by atom. And again, while superconducting circuits 20 years ago were pretty classical objects, nowadays we really have quantum objects on large scales of many qubits. And we can realize, I mean, these platforms realize really strong nonlinearities so that you can have genuine many-body phenomena. So the question is now what kind of many-body phenomena we can have in these different regimes that people are being exploring for several reasons, computing and other technologies as well. So, well, in particular, I will talk about driven dissipative systems as a new route to quantum phases. I'm putting new in quotes because this is not really new. This is what people in quantum optics have been doing all the time. So instead of looking at ground states, in quantum optics, you take typically atoms, which have optical transitions, and you shine a laser, the atoms couple to the vacuum, so you have dissipation, so you reach a steady state after some time where the two balance, and this is not an equilibrium state, it's not a ground state. So in which sense new, again, is the new part is that now we can really have steady states on macroscopic systems retaining correlations across. The situation is also interesting for several reasons. I mean, the kind of physics that emerges here is different because, of course, dissipation can steer the dynamics in a different way than coherent dynamics only would do by shedding some excitations over the system and not others. So you can really use this tool. I mean, it can really give rise to different things from what you can achieve in ground states. Okay, so this was a pretty broad introduction. I hope you're still there. I heard a strange noise.
Yeah.
Okay, good. Because I can't see I see the presentation slide on both screens, so I cannot see if you're still there. Okay, good.
We're here.
Yeah. Okay, so after this quite broad and maybe useless introduction, let me get to what I want to talk about today, which is the problem of quantum emitter arrays. I'm sure some of you have heard already about this. So this is a quite general problem, I would say, of a set of quantum emitters that interact together. So quantum emitters are some quantum systems with some discrete energy levels that couple to the electromagnetic field, here the vacuum, and this vacuum induces something on the emitters, for example, spontaneous emission terms, but also dipolar interactions. And in particular, when you bring the atoms close, the dipolar interactions become strong, and so you can have, in fact, strongly interacting regimes of the emitters. So I will use this master equation formulation of the problem in which the vacuum field, which all actually an important thing is that here I want to consider regular geometries of the emitters with the spatial with some arrangement in space. So differently from, for example, a decay model here, I have really a lattice geometry that I need to take into account. So each emitter couples to the field differently. And here, this description really comes from microscopic description of the vacuum field, which is integrated out and gives rise to two terms which couple different atoms. This is the correspondent dipolar interaction term, and this is the decay rate of the atoms. Notice that both terms here they are non-local. In fact, they come from the real and imaginary part of the vacuum propagator, these expressions here. And therefore, you do not only have interactions between different atoms, coherent interactions, but also you have collective decay effects. Namely, you can have interference between different emitters that emit simultaneously. Finally, in this kind of setup, you usually have some driving. You can have some driving field that excites the atom, which is this term here, where KD is the momentum of the driving, therefore the direction at which you're driving, essentially with your laser. One thing I wanted to notice is that these couplings here have a structure fairly complex. In particular, these coefficients alpha and beta will depend also on the direction at which you drive, at which the electric field oscillates, which induces the direction at which the dipoles oscillate. But the main thing I will discuss is the one thing I wanted to notice here is that this scale has power laws. So these are power law decaying couplings, so they are pretty long range. There are several experimental platforms that implement this model. In particular, I'm interested in ultra cold atoms, which typically are trapped with optical lattices or also tweezers, where these two-level atoms in this case are real atoms. But also there is nice experiments with semiconductors and excitons, in which the excitons essentially are the two-level system. These can decay by emitting a photon, so it's really the same model.
Sorry, Orazio.
Yes.
The one with exciton is one dimensional, or they can do it also two dimensional.
You know that I don't remember whether it's one or two dimensional in the experiment. I think I'm not sure. I'm not sure because for sure the semiconductor system is a double well is two dimensional, but I don't know. So the potential comes from some potential that they apply. So I suppose they could do both one and two dimensional, but I don't remember honestly the experiment what it is.
And I mean, even if it's 1D, can they make it like very large atomic arrays, like the one with ultra cold atoms in tweezers,
Well,
or they are limited with size?
I would say size is not a problem here. Actually, they are much better for what I will tell you of making this arrays wavelength. Because they are really sub-wavelength and they observe all the physics that people would like to observe with atoms, where making atoms close is difficult. The problem that they have there is that, well, perhaps they have a little less control. Well, okay, I would say, it's a pretty good experimental setup. I don't think it's in size it's worse than the atoms.
Okay.
But okay, I don't off the top of my head, I don't have the numbers of how many sites they have. But
Yeah, sure. It was
it's
just
not limited in that.
curiosity.
Yeah. This experiment is very nice. I was surprised to discover this. So they see really signature of collective phenomena like the subradiant modes. I will talk about later. So yeah, please interrupt me if you have questions. I encourage that. So yeah, this is the system I want to talk about. I will try to analyze. Yeah, the orientation of the dipoles will not be crucial for what I will tell you in the following. So the key control parameter that I want to have in mind is essentially the ratio between the lattice spacing and the wavelength of the transition. This enters via this parameter K0A, which essentially enters in all these arguments here of the couplings. And this essentially controls both the relative strength of dipolar interactions and dissipation. So when this parameter is small, when you are very sub-wavelength, then the dipolar interactions dominate, and you go towards a closed system scenario. At the same time, interactions and dissipation become more long range, and in particular, dissipation becomes collective when you are really sub-wavelength. Well, I shouldn't say collective, become all to all when you're very sub-wavelength. But it's also true that is really subdominant in that limit. But so the take-home point is that if you make the atoms closer, the coherent interactions will become stronger and dominate over the dissipative nature. Well, indeed, there is a whole bunch of phenomena that can happen where the atoms behave collectively, such as superradiants and subradiants, which are classic examples. But really here in these platforms, now they have both geometrical control, and if you can make the atoms close, you can also get to control interactions, which is really driving a lot of search for interesting applications of different sorts. You can control essentially the collective behavior. In these papers, for example, they talk about quantum metasurfaces, that is surfaces that can help you control the degrees of freedom of light passing through. And I think it's a very nice set of experiments. So what I will focus here, what I want to look at is instead, is a bit beyond what has been done in experiments so far. That is genuine strong correlations physics. In fact, most of these experiments probe mostly linear response, while I would really want to understand the many-body physics and the physics in which quantum correlations play a role. So for this, one has to ask what kind of theoretical approaches we can use. And in fact, it turns out that there are not so many because, well, this is a out of equilibrium driven distributive parallel interacting many body system. So it's pretty bad. And therefore, the techniques that have been used are, of course, Gutzwiller mean field techniques, cumulant expansions, where you truncate the hierarchy of correlation functions, and also truncated Wigner. The second is a bit is often unstable. Truncated Wigner, it's good when you're close to semi-classical regimes. I would say all of these techniques somehow break down when you have strong enough correlations. And there is possibly no to-go technique, even the one I will talk about. But here I'm showing also a phase diagram obtained with, via Gutzwiller mean field. So this neglects correlations, assumes a density matrix which is factorized. And here you see that as a function of drive strength and detuning, there is a lot of different phases with different orders. Some are limit cycle phases, some are spin density wave phases. This kind of tells me that there is potentially a lot that can be realized in the systems. On the other hand, this is a Gutzwiller study, and in these regimes, correlation might be really important. So we really need to understand better what's going on here and get more intuition apart from a summarizing phase diagram like this. So this somehow motivates what I will tell you. So first, I want to introduce another approach to study these systems, which is based on things that I've developed in the past, I've studied and I've worked on in the past. This is a dynamical mean field theory approach, which comes from the field of strongly correlated electrons. And then I will use this approach to study two physical phenomena in the system. One is the spectrum of emission of the system when you drive it strongly. And the second instead is the regime of weak driving, where I'll try to convince you that there is some interesting correlated steady states. So, well, maybe I should ask here if you have any questions on the setup on the things I've discussed so far.
Maybe Orazio, can you just briefly mention you said that plot was used was made with Gutzwiller mean field.
Yes.
So just briefly, can you just say a few words on how that works? Just maybe very quickly if you can.
You mean the technique or the results?
Yeah, no, that technique is like what are the basic assumptions? Just for
Gutzwiller mean field is just the, let's say, basic Ising, classical Ising mean field in which you decouple nearest neighbor interactions, or I mean two-body terms, assuming that essentially one side feels the others as an average. So you assume that your density matrix is factorized. So here is done at the level of density matrix. So it's a very
clear. Okay.
Very basic approach. Yes. So okay. So this is a bit the plan. Let me go through through the different points. Let me first give a brief introduction to DMFT, which I will then apply. So I don't want to be exhaustive here. I'll just give some idea of what this is like. So this is an approach that as I was saying, was developed for strongly interacting electrons in the early 90s. So here I'm writing a Hubbard Hamiltonian just to have this in mind. And this is a Green's functions based approach So the goal, the first goal you want to have is computing the single particle Green's function your fermions. Here I'm just omitting the spin index for simplicity. So what DMFT assumed is that the self-energy of these green functions, that is the or of the problem, that is the part that takes into account the nonlinear term, so the Hubbard U in this case, the self-energy is assumed to be local in space, while this still has some dependence in time. Here I will always talk about real time because I will concentrate on the non-equilibrium version of this approach. So this is one assumption, self-energy is local. If the self-energy is local, then from the self-energy, you can compute your Green's functions in a standard way, in particular the local Green's function. Then the second assumption of DMFT really is that you can map the original lattice problem, so the problem in a certain geometry, onto a single site model in the space of a mean field approximation, where the effect of the neighbors is encoded in some effective buff. So this is an action description where the buff comes as a retarded interaction between the fermion fields. But you really should think about this as a buff of non-interacting particles, in this case, fermions. So once you have mapped if you assume that you can compute your local quantities, in this case, both the self-energy that you assume that is local and the Green's functions, then you get a self-consistent condition to determine this buff here. In particular, if you can solve the dynamics of this problem with this, in principle, very generic buff, and you can compute the Green's function. Yes. Okay. Yeah, I thought there was a question. So if you can solve the dynamics of this model, of this single site problem with this complicated buff and get the Green's function, then this also gives you the self-energy in a very standard way. But this Green's functions, this Green's function also has to satisfy the equation 1, which comes from the original problem, and therefore this equation gives you a self-consistent condition for delta. So you solve this problem at fixed delta, and then by imposing equation 1, you determine delta such that everything is self-consistent. So this is very similar to a standard Ising mean field or Kutzwiller mean field, except as a concept, except here the self-consistent thing is not only a scalar field or a field which has only one time, but is really a function of 2 times here. And yes, so this is more or less how one can understand DMFT as a useful approximation. The thing is that these assumptions that might seem completely arbitrary, and to some extent they are, actually become true in the infinite dimensional limit of fermions, or they will introduce the 1 over d, where d is dimensionality correction in the case of bosons or atoms, as I will talk about. So there is a limit in which these assumptions are actually very physical, which means typically that this approach will work when you are in high enough dimensionality. In practice, 3D is usually good. 2D, you miss a lot of 2D physics related to geometry. 1D, you have to be careful. But yeah, in the end, you can use it in all dimensionalities, keeping in mind that you might miss important geometrical information in lower dimensionalities. So this is a general, let's say, introduction to DMFT. Let me say how this generalizes to the case of the atomic arrays. So this is a bit non-standard. Is a bit of a non-standard application of DMFT because these are spin degrees of freedom, which usually are very nasty to treat in field theory or Green's function approaches, because a spin doesn't have any non-interacting limit. But so what I've been doing in this publication here is generalize some approach that was proposed in this paper by Martin Eckstein in 2022 in an equilibrium case. So the thing goes along these lines. You first map the master equation on a spin-Keldysh functional integral, which can be done in some standard way, with the caveat that here you're treating spins and not bosons or fermions. But actually, the fact that the spin is particularly complicated to treat in an action formalism here is actually bypassed by the fact that one introduces some auxiliary bosons that couple to the spin. So in particular,
sorry, Orazio, the auxiliary bosons are the sigma, right?
The auxiliary bosons are the phi's, while the spin is this z. I call it z because it's actually a vector of spin operators, but yeah. So the bosons is the sigma. So essentially, the point of this transformation is that you can decouple the terms, the knowledge in terms of the spins, such that these terms, the dipolar interaction and collective dissipation, enter in a free boson propagator now, while the bosons only couple to the spin locally. So why this is interesting? Well, because bosons have a non-interacting limit. So this is a free boson. Now the coupling to the spins, essentially, you can see it as entering in the self-energy of the bosons. So it's a term that gives you some nonlinearities on the bosons field. So if you followed till now, what it means is that now I can use bosonic DMFT to treat the bosonic problem with DMFT, where the spin is something that gives me some linearities, but enters only locally. So essentially, it's in this DMFT formulation, it doesn't really create any complication. So said in other words, I never evaluate the spin dynamics in the functional integral approach, because in the end, I only solve a local spin problem by some other approach. And this enters in this effective boson problem as a self-energy. So I hope I could convey the spirit. So in the end, let me just go through this. Once I have this boson spin problem, then I apply the DMFT. This problem is mapped onto a single boson and single spin problem, which is in the spirit of what I told you before about DMFT. And then eventually it's handy to integrate out to the boson again, such that you get a single spin problem coupled to a retarded interaction, which is the DMFT buff that I was telling you before. The difference from there is that not only you have this, you also have this term, which is the conventional, let's say, effective magnetic field on the spin, which you get in Goods-Wheeler mean field. And in fact, in this case, this is a bosonic DMFT. The effective buff gives you 1/d, where d is the dimensionality corrections to the Goods-Wheeler mean field, which is only, is obtained retaining only this term. So this method essentially allows you to go beyond mean field while retaining 1/d corrections at the action level.
So in this impurity spin-only model, you basically have integrated out the bosonic degrees of freedom?
So it's more than that. So I start with this model on a lattice, which has bosons and spins. Then I do a DMFT. Then I do a DMFT. The DMFT maps the lattice model onto a single side, and then I integrate the bosons. The boson. Okay.
Yeah.
So this last step is just for convenience, because in the end, I will solve this in some way, and I prefer having only one spin than a spin and a boson. Yeah. And in fact, the last bit is, well, how do I solve this problem now? So suppose I give you this problem of a spin coupled to a terribly non-Markovian buff. How do you solve it? Well, you don't solve it in general. What I'm using here is some sort of approximation, which is typically used in non-equilibrium DMFT approaches. Here we had extended it to a case in which your underlying dynamics is Markovian. But to give you a feeling of what it is essentially an expansion in this self-consistent in this DMFT bath, which represents the effect of the neighbors. Therefore, and then this is treated in self-consistent lowest order perturbation theory. But essentially, this approach, this way of solving the single site problem will work when the effect of the neighbors is small enough. Which means that in really collective regimes, this approach, this approximation will break down. Not the DMFT, but this last approximation, this non-crossing approximation, will break down, as will happen in the things that I will show you in a second. Okay. So this is all I wanted to tell for about the method. With time, Federico?
I mean, you still have 25 minutes.
Okay, 25.
I mean, it's
okay.
roughly 1 hour, so.
Okay. Good. So I'll hopefully, maybe I can speed up a bit on the physics part. But yeah, if you have questions on this, maybe you can ask now or later. Now I will switch to two physics cases. So yeah, I mean, if you're not familiar with this kind of methods, is essentially a method that allows to go beyond mean field and retain some correlations between the atoms. Essentially, I mean, really both statistical and quantum correlations, such as entanglement. So okay. So now that I have this method that well, I tried to generalize for this problem. Now I kind of have the ingredients to study the physics of this. So I'll first talk about the spectrum of emission of the problem. So this is typically something that you want to measure in these setups. You put a photodetector somewhere. You have your atoms array, and depending on the angle at which you detect the photons, you can essentially look at different you can have momentum and frequency resolved measures of the correlations of the electric field that arrive at the emitter. So here I will consider the strong driving regime. So the regime in which you're driving is stronger than the losses. This is a bit of a simple regime with respect to the full many-body problem, because essentially when the drive is strong enough, you find that the steady state density matrix just becomes featureless. It becomes an infinite temperature state. So you don't have any correlation in the steady state density matrix. Nevertheless, you can still have effects of quantum effects in the emission spectrum. This is something that people know very well in quantum optics. And in fact, for a single atom, what you get is this quite famous mollow triplet spectrum. So here this is the plot which is shown here from this paper of 69 of mollow. So this is the spectrum of a single atom, the light scattered from a single atom. And you see here that, the different curves correspond to different driving strengths. So when you drive the atom very weakly, this is on resonance, resonant drive, then as you expect, you get only one peak in the emission, which corresponds to the atomic frequency. But when you start driving stronger, then you start having these sidebands. So the spectrum is a triplet. Well, why do you have the sidebands? Is because there is some hybridization of the light that you're sending on, the laser light, and the atom itself. So you are probing the discrete nature of the atomic spectrum, which gives rise to this triplet. Here I'm trying to go a bit explain a bit more in detail how this comes about. So this on the left, you have this so-called dressed atom picture proposed by Cohen-Tanucci and Raynaud. in which you assume that your laser field is a quantum degree of freedom, is a single boson, because more or less it has a fixed frequency, a well-determined frequency, determined frequency, and you assume that this mode is highly populated. So if you look at this Hamiltonian now, you immediately see that the total number of excitations, both in the atom and in the spin, and in the boson, is conserved. And therefore, the eigenstates are this symmetric and antisymmetric combination of the excitation being either in the atom or in the boson. So these are doublets, and you have these for any number of excitations in the system, essentially. So if you look at the spectrum as a function of energy, you have these doublets, which are spaced by the coupling with the laser, essentially this Rabi frequency, which is related to this coupling G. And the doublets are spaced by the frequency of the atoms. So you have these doublets, which correspond to having n excitations in the system. And then, so far, these doublets are disconnected. But then, I don't know what happened. I lost the presentation. Let me share it again.
Okay.
So these doublets are not coupled by the Hamiltonian, but then you have spontaneous emission. You have the dissipative part that indeed can make you lose excitations. But now you have to connect one doublet. If you lose an excitation, you can do it in essentially 3 different frequencies. You go this way, and then the frequency you get is the atomic frequency, or you go these other 2 ways, which is the atomic frequency plus or minus big omega, which gives you these second peaks and side bands of the triplet. So this is a more physically oriented picture. Even if you treat the light classically, this is actually very simple to see. If you are on resonance, the only term you get is a sigma x Hamiltonian in a rotating frame. So these transitions that I showed here in this rotating frame, in which you have to shift frequencies by the atomic frequency, so all these doublets somehow collapse on a single doublet, and the dissipator can make you do transitions between 2+ or 2- states, or in between them. And so you get this, again, this mollow triplet thing. So these 2 are equivalent. I will use the second one. Physically, I think the first picture, in which you don't go in a rotating frame, is a bit more intuitive. Okay. So this is what happens for a single atom. So let me now try and find out what happens for many atoms, as far as I could. So if I have a collection of atoms and I disregard the interactions, then my Hamiltonian is just the sum of sigma x's. So the many-body states, eigenstates, are just product states of sigma x eigenstates. So these are organized in a ladder with where essentially with fixed number of flips that I have in the state. So the first one is all pluses.
Sorry,
in the second,
Orazio.
yeah.
Are you neglecting the dissipation because you're still in the limit of omega much larger than gamma?
Well, I'm not neglecting it. I'm just looking at the spectrum of the Hamiltonian for the time being. I will be in the large drive regime. So omega will be very large compared to the dissipation.
Okay.
But okay, so far I'm just looking at the spectrum of the Hamiltonian. Then I will solve the full thing with the DMFT. But so far it's just to motivate. So yeah, I'm just looking at the spectrum of this part and try to, essentially show you that it's not trivial to then incorporate the effect of interactions, even if we are in this infinite temperature steady state regime. So yeah, the eigenstates are organized in a ladder, and each level has a fixed number of excitations in the system. And here, then the transitions that contribute to the mollow triplet are essentially the same transitions as before, but between each two levels, adjacent levels of the ladder, which corresponds to losing one excitation in the system. So you have to somehow gather all these transitions, and these will give rise to the modified mollow triplet in the many atoms case. Okay, so then, of course, I want to turn on interactions. What the interactions will do is that they will shift these energy levels, and therefore these transitions will not happen between two precise levels as before, but they will essentially occur as if they were occurring from two bands. So the effect that I expect on the mollow triplet is that these three peaks that I had will be broadened by effect of the interactions. Here, note also that I'm keeping the interactions also small compared to the drive. So this might be comparable or larger than the dissipation, but they will be smaller than omega, which means that I still have this ladder structure, but I have some broadening here of each of these levels. The one thing that I want you to notice is that, well, although you have this ladder structure, etc., to really resolve the real shape of the spectrum of the triplet, you still have to, well, diagonalize the Hamiltonian in each of these sectors. And towards the middle, I mean, these sectors are n choose n, where n is big N is the number of atoms and small n the number of excitations, and this goes exponentially towards the center of the ladder. So you're still dealing with an interacting, with an exponentially complex many-body problem, which makes this problem, although simple from the steady-state point of view, still complicated. Okay, so I will attack this with the DMFT I introduced before, where I can compute the atom correlation functions. In particular here, if I take a Fourier transform in space and time, I get them as a function of momentum and frequency. And this directly translates in the spectrum of the light emitted in the far field. So here is what I get then from the DMFT approach. So this is a DMFT spectrum in the steady state. Everything is taken into account. So the full model that I showed you. For the time being, concentrate on the solid lines. Different colors here correspond to, so the gray line. So this is the propagator I just told you. In particular on a single side of the lattice, but this will be representative of all momenta. I will tell you in a second. And on this axis, you have frequency. So this is spectrally resolved. And the different curves are for different spacings of the atoms. So from the gray curve, where you have the single atom, then I bring the atom closer, and I get the green, red, blue, with the larger broadening the closer the atoms. And well, the one thing that is quite striking here is that, as you see, the three peaks broaden very differently. The central peak remains kind of peaked at the center, while the side bands become very flat. So this is...
Sorry, Orazio, the single atom case, the gray one, it's the original one by Mollow that you showed before?
Yes, except here I'm showing in logarithmic scales because you see better the shape.
Okay.
Because otherwise the central peak is much higher than the others.
So this is kind of a many-body Mollow triplet in some sense?
Yes, yes.
Okay.
Yeah. Yeah, the striking thing, or curious thing, is that the broadening is really structured. In fact, this is not a simple density of state effect as the one I was trying to show you here, because if you have this picture in mind, I mean, this is true, but if you really believe this is true, then the three peaks should broaden in similar ways. So this is an effect which goes beyond the density of state in the many body problem, and it's really related to the matrix elements between the eigenstates, essentially. Yeah, to be fair, I don't have a very clear explanation to the, well, a very exhaustive explanation of why you get this structure. What we could see is a number of interesting things. So the first is that this broadening is clearly correlated with the dipolar interactions. So it is an effect of the dipolar interaction. Here in this plot, I'm trying to show this. I'm showing how this the broadening, the width of these sidebands grow as a function of the spacing between the atoms, A. This line is the scaling of the nearest neighbor interaction, which is the strongest. And you just say that they have the same scaling. So the interactions are responsible for this, while the collective nature of the decay rates does not really play a role on this. I mean, you really need dissipation, but the fact that this collective doesn't seem to be really important. I suppose that's because we are in a strong driving regime where there is a lot of noise, and somehow the dynamics should be fairly local.
Can I ask a quick question?
Yeah. Yes, sure.
I guess theta here is the direct related to the emission direction.
Is the polarization of the field?
Oh, sorry. And what about? Oh, okay.
Yeah, I'll discuss these things in a second.
Okay.
Well, polarization is not really crucial. I will discuss the. Well, I mean, it is somehow. I will tell you about this.
Okay. Thanks.
Okay. Yeah, another thing is that you need the atoms to be ordered to get the structured broadening. This is a study done on some disordered cloud. Although it's a small number of atoms, they kind of claim this is well converged somehow. But okay, the point is that in this case, you see a broadening, of course, because you expect that, but it's not. It doesn't have any structure. So somehow the local ordering of the atoms do matter. So coming to your question, how does this depend on momentum? That is the direction of emission. Well, pretty strikingly in DMFT, this does not depend at all on momentum. This is partly an artifact of DMFT because it neglects some geometrical information, but it's still non-trivial. So I do expect momentum dependence in DMFT, while this particular function in this particular regime doesn't have one. So I will try to convince you in the next slide when I compare with exact diagonalization that this is not completely an artifact, but it's actually kind of true. The second thing is that here I'm considering I am considering not only a 1D geometry, but also different geometries, 2D square lattice and triangular lattice. And you see that all the curves essentially collapse. Collapse when I scale them such an effective interaction parameter, which is the geometric mean of all the interactions in different directions, which are anisotropic. This depends on the polarization here that I choose. But it seems that the only thing that matters is really this geometric mean. So if I define an effective lattice spacing such that this is constant between the different geometries, I can collapse all the curves. So this somehow is telling me that there is some sort of generality in this spectrum, and it doesn't seem to depend really on momentum or even on the details of the lattice. In this other plot here, I'm trying to say the same thing by changing the polarization. And again, you see the same kind of behavior. There is a particular lattice geometry in which this thing doesn't change. Is the triangular lattice here, where all the red curves are superimposed naturally, and this is how I realized that this might be an important parameter. Yeah, unfortunately, I don't have a deeper intuition of why there seemed to be such a robustness or generality of this structure. The last want to show you is a comparison with exact diagonalization. This I did it in 1D, which is even the worst case scenario for the MFT. And here is now is a resolved picture. Well, you see that while there is some momentum dependence, the overall structure is kind of well captured by the MFT. You have this flat side bands and a central peak, except close to k equals 0, where there is some emerging symmetry at that point, which really makes that these matrix elements are collapsed at the center, as you see here. So somehow this point is very non-generic. While at finite momenta, it seems that the MFT predictions, even in 1D, are pretty much okay-ish, I would say. So yeah, this is all for this set of results. If I still have 5 to 10 minutes, I can go through some other results.
Yeah, sure. We still have 5-10 minutes.
Okay. So yeah, perhaps let me go through those a bit quickly, and then you might ask questions on both parts. So so far I talked about a strong driving regime. So this is a pretty different scenario. So you can forget I told you about mollow triplet. Now I want to look at weak driving. In this case, you can have steady states which are non-trivial. Technically, this is a quite harder regime in which all the methods struggle, including the DMFT because it becomes very collective, and the approximations that I do at some point break down. But let me show you what happens here, because I think some results are pretty nice. So first, how do I think about the weak drive regime? How do I think about it? What I want to argue here is that if the driving is very weak, this essentially maps onto a non-interacting boson problem. You can literally replace the spin variables, the spin annihilation operator, with bosonic annihilation operators. And because if the driving is weak, essentially your occupation is small and you never explore higher the nonlinearities of the spin Hilbert space. And you see that since these terms in which two spin operators appear are only quadratic, then you get a quadratic bosonic problem, which can be diagonalized and solved exactly by introducing collective modes. So this description holds. Suppose you're driving resonantly one mode and you're driving it with a strength which is smaller than the decay rate of that mode. Then in this regime, this is a good description, because essentially your excitation doesn't live long enough to experience any scattering via the nonlinearities before being ejected by the dissipation. So for this reason, essentially, a very long list of works have kind of formalized this idea and analyzed this weak driving regime with essentially a classical model of or a model of non-interacting bosons. So what I want to argue here is that in the case of regular arrays, this is actually not really a good picture. But before making that claim, let me introduce another element which I need, which is subradiant modes. These are modes that appear when you are in subwavelength conditions, that is, very closely spaced atoms, that have very low decay rate compared to the single atom decay rate. And they appear because of interference effects, because of interference of the emitted light by the different emitters that in the far field sums to 0, essentially. For this reason, these modes are very interesting for applications such as quantum memories or even metrology, because they have very narrow line width. And therefore, from what I told you, what I told you before of the weak driving regime being linear, it's natural to ask, don't these modes actually contribute a lot when you drive weakly? They have so small decay rates. Well, no, because as they don't emit photons, they also are decoupled from driving fields. And therefore they are kind of shielded from any electromagnetic radiation, and therefore they are not excited if you drive weakly the system, or at least this is what one might a bit naively think. And in fact, there is a long list of proposals to try and pop them at least at single excitation levels. So this is kind of a general picture. Even for disordered ensembles, you still have these decay rates. But here I have concentrated, and I will concentrate on ordered arrays. And these are quite special for a very simple reason. But first of all, let me tell you of a very simple picture of why these subradiant modes arise. So this is the dispersion relation, the yellow curve, and collective decay rate for the case of array, where you have conservation of lattice momentum. So your collective modes are momentum modes. You see that the decay rate, this blue curve, is essentially zero at large momenta. And this cusp is at a point which depends on the spacing of the atoms. Actually, these decay rates scale as a for open boundary conditions in the number of atoms, or as an exponential even for periodic boundary conditions. So as I don't have much time, let me quickly go through this. So these appear because essentially, if you compare the excitation energy of these, the energy of these excitations with the dispersion of free photons, then at large momenta, the free photon dispersion is very steep. Dispersions cross. The excitation at large momenta essentially are strongly mismatched with the photons and cannot decay into free photons. So this is the reason why you have these manifolds at large momenta that are dark. Okay, but then if you have this momentum, very, very nice momentum structure of these modes, what I've been asking is, well, can't I then excite these subradiant modes if I cannot drive them resonantly in a linear fashion, but can I excite them resonantly non-linearly? So for example, here, I will consider a driving which is orthogonal, a laser which is orthogonal to the array. So the incoming momentum of the photons along the array is zero. I'm thinking about some processes in which two or more than two photons essentially effectively scatter into excitations with the opposite momenta, these subradiant modes. And these processes will conserve energy and momentum, and therefore, they are resonant processes, although they are nonlinear, so they can they can matter and have a strong effect. So this is the kind of scenario I have in mind. Since I'm running out of time, so what I want to tell with this slide is that one can somehow rationalize what these processes are. It assumes a low density of excitations and uses a bosonic representation of the spin. Then, okay, you can write down in time-dependent perturbation theory what these processes are. Second, we tried to include these modes, the effects of these nonlinearities, doing a sort of weakly interacting Bose-Gas approximation. So I assume that the effects of the interactions are small, and therefore I first solved the problem without the interactions, where the only mode that populates is the k=0 mode, because the laser is at k=0. And then I turn on the interaction, so I impose this expectation value for the bosons at k=0, and I get an effective model for the subradiant modes that are now resonant. So these coefficients here, they depend on the drive strength, because this comes from this guy. So I'm assuming the drive strength is a small parameter. In principle, you also get corrections in the dissipator, but the decay rate of these modes is already suppressed by the number of atoms, so you can disregard these further smaller terms. And so what you get from this analysis is essentially that, well, this model is a parametric amplifier, a standard parametric amplifier model, is unstable as soon as my drive strength is larger than the dissipation rate of the subradiant modes. And this is very small in the number of atoms. So essentially, even for very weak drives, this model will become unstable, and the number of excitations in these subradiant modes will only be bounded by nonlinearities. So I cannot really neglect nonlinearities or treat them at this level. And I will get some steady state which is non-perturbative, because here the population really, when you're beyond parametric instability, your populations in the steady state diverge. The model is completely unbounded. The dynamics is completely unbounded. So this motivates then using again the DMFT. So this is the occupation of the steady state as a function of momentum. And here I'm scaling the drive frequency to be resonant with the dispersion relation at different points. And well, you see here that at these points you have no excitations, well, here, because there is no states, but you get a population of these branches which correspond to the subradiant